All right, just take a look around you for a second. Chances are you're looking at concrete. It's everywhere, right? It's the silent giant holding up our entire world. But what if I told you this stuff, this totally ordinary material, has a secret life? And that secret, well, it could be a massive game changer for our climate.
Okay, so first, let's get the bad news out of the way. This is the part we probably all know. Cement, the key ingredient in concrete, is a huge climate problem. I mean, its production accounts for more than 6% of all global CO2 emissions. That is an enormous number.
But here's the thing. What if that's not the whole story? What if there's a twist? And what if concrete isn't just a climate villain, but maybe, just maybe, it's a secret hero too?
All right, so let's start by digging into the problem. Just how big is this climate footprint we're talking about?
Get this. Every single year, the world churns out so much cement that it releases over 2.5 gigatons of CO2. That's gigatons with a G. It's a footprint so big, it's actually kind of hard to wrap your head around.
Okay, but now for the secret I mentioned. The really interesting part of this story actually begins after the concrete is poured, because this is where it turns into, well, a carbon sponge.
So, when you think of a block of concrete, you probably think it's just solid, inert, dead, right? Well, wrong. It's actually alive with chemistry. For its entire life, it's quietly breathing in CO2 from the air around it and locking it away inside.
The scientific name for this is carbon uptake, and it's basically a chemical reaction where CO2 from the atmosphere reacts with the cement and turns into a solid mineral. So yeah, it's exactly like a super slow-motion sponge just sitting there soaking up carbon for decades, maybe even centuries.
And just to be clear, this isn't some weird thing that only happens in a lab. No, it's happening right now, literally all around us. The walls of the building you're in, the bridge you drove over today, the sidewalk you walk your dog on. Every single one of them is acting like a carbon sponge.
Now, scientists have known about this sponge effect for a while, and some of the early, broader estimates were pretty wild, suggesting it could soak up over half of the emissions from making the cement in the first place. But a really groundbreaking new study is revealing a much more complex and, honestly, a much more fascinating picture.
And that brings us right to the heart of this new research. When it comes to concrete absorbing carbon, it turns out context is everything.
So a team of researchers at MIT decided to ditch the broad global estimates and do what's called a bottom-up study. They looked at thousands of different combinations of specific building types, different materials, even different local climates. And this is a huge deal. This new level of detail is giving us the most complete picture we've ever had, and it could totally change how we think about building sustainably.
Okay, so first things first, where does all the cement actually go in a building? Well, take a look here. In your typical building, a whopping 3/4 of it goes into the really massive stuff. Foundation slabs, floors, which makes total sense, right? The big, thick structural parts, they're going to need the most material.
But now, get ready for the plot twist. Look at where the carbon uptake is actually happening. Those giant slabs, they're only responsible for about 1/4 of it. The real hero of this story here are the concrete masonry units, or CMUs, cinder blocks. They absorb over 30% of the CO2, even though they use less than 10% of the cement. How cool is that?
So what's going on here? What's the secret? Well, it turns out it's not about how much concrete you have, it's all about the surface area. Those porous masonry blocks, those CMUs, they act like super sponges because they have so much surface exposed to the air. That's what makes them so ridiculously efficient at soaking up carbon.
And this just hammers home that point about context being king, because different places use different construction styles, different materials, and have totally different climates. The amount of carbon their concrete absorbs is all over the map. I mean, just across the US, there's a fourfold difference from one state to another. That's huge.
But to really see the power of context and action, let's look at a tale of two countries.
Okay, so the study found that in the United States, all the concrete we already have reabsorbs about 13% of the cement industry's annual process emissions.
Now I know, 13% might not sound as impressive as that old 55% estimate, but trust me, it is still a massive climate benefit. We're talking 6.7 million metric tons of CO2 every year. To put that in perspective, that's like taking 1.4 million cars off the road every single year.
All right, now check this out. This is where it gets really interesting. The US uses about twice as much cement as Mexico, so you'd think we'd absorb more CO2, right? Wrong.
Mexico's concrete absorbs about 25% of its industry's emissions. That's nearly double the rate of the US. So how is that even possible?
You guessed it, it all comes back to context. Construction in Mexico uses way more of those super spongy CMUs and mortar, especially for houses. Their building practices are just set up to maximize the surface area that's exposed to the air, which makes their concrete basically twice as efficient at soaking up carbon.
So the big question is, what does all this mean for how we build our future cities and towns?
Okay, so let's break down the key takeaways here. First, this carbon uptake thing, it's real. It's a measurable climate benefit. Second, how and where we build matters a lot. And third, even when we tear a building down, crushing up that old concrete exposes new surfaces, giving it one last big gulp of carbon absorption. Now look, this doesn't make concrete carbon neutral. It's not a silver bullet, but it absolutely makes it a much more valuable player in the climate fight than we've been giving it credit for.
And like the authors of the study said, we can actually design for this on purpose. Their words were, enhancing carbon uptake is a valuable strategy to add to the arsenal. That means we can start intentionally choosing materials and designs that really max out this amazing sponge effect.
And that really leaves us with a pretty mind-blowing final thought, doesn't it? We've always thought of our cities as these huge sources of carbon. But what if that's not the only way? What if we could actually start designing them from the ground up to be giant, slow-motion carbon sponges, actively cleaning the air for centuries to come?